In this lecture, you will learn about a particular type of computer models that we can use to study social self-organization. These models are called cellular automata. You have already learned about agent-based models. Cellular automata models can be seen as a particular class of agent-based models. In the following, we will discuss the basic principles of a cellular automaton model. The first important principle of a cellular automaton is its spatial structure. A typical example is a checkerboard structure like the one you see here. Every cell in this structure is a location, and this location can be a position where an agent representing an individual is settled. We also call this a cellular world. You can think of this as a very abstract and simplified model of how people live in a city. A cell represents the place of a house or an apartment. The household or the individual living in this cell has neighbors on each side. Social self-organization in a complex social system arises from the local interactions of individuals with each other. In a cellular automaton model, we can give a precise meaning to what we mean with this local interaction. Local interaction is the second important principle of a cellular automaton model. It means that individuals can only interact with others in a close distance around them. For example, in the abstract city on the checkerboard, you may only talk to the neighbors in the cells that have a common border with your cells. Here you can see different types of neighborhoods that are often used in cellular automaton modeling. In the leftmost picture you see a so-called von Neumann neighborhood. Here the cell in the center has four neighbors, one to the north, one to the south, one to the west and one to the east of its own position. In the next picture you see a so-called Moore neighborhood. Here you have 8 neighbors. So also the neighbors on the corners bordering to your cell are your neighbors. And we can make this neighborhood bigger, like in the 5x5 Moore neighborhood that you see in the rightmost picture. This difference between these neighborhoods can be seen as a model of how local the interaction is. In the leftmost von Neumann neighborhood, you have the most local interaction. You interact only with a few neighbors. In the rightmost, you have quite many neighbors, and of course, we can build in a lot of variation in how exactly we will model these neighborhoods. You can think of the example of the spreading of a rumor. In a von Neumann neighborhood, people would only talk to their nearest neighbors. In such a world, the rumor would spread only very slowly. But in a Moore neighborhood, you have more neighbors to talk to, you have more neighbors from whom you can hear the rumor, and it will spread faster because it can come from people who are more steps away from you. Of course, there can be many other ways to model neighborhoods, like in the example that you see here. And as you see in this example, the red neighborhood is more local than the yellow one. So in general, the way you model the neighborhood can be used to express how local or global the interaction in your model is. This can be used to model effects of conditions like communication technology or geographic density of a population on the outcomes of social self-organization. So far, we have seen 2 important principles: the spatial structure and local interaction. But how can we model what happens in interaction in a cellular automaton? For this, there are again 2 basic principles. The first principle is that agents in the cells have a state. The state represents, for example, their opinion or their ethnicity. Typically, a state is modeled as a number. So, for example, an agent may have the states 1, 2 or 3, representing which out of 3 possible political parties the agent would vote for. The second important principle is that states can change. Agents can change their states. how they change their states depends on both their own state and the states of their neighbors. So for example, if the majority of your neighbors believes a certain rumor, you may also start to believe it. But when can a state change occur? There are different ways to model this. Time is discrete in cellular automata models. That is, time moves on in steps or rounds. In some models, all agents change their states in every round at the same time. They take their own state and that of their neighbors from the previous time point and then all change to a new state. In other models, one agent at a time can change his state depending on the current situation. Typically, agents are then selected at random for a state change. Moreover, we distinguish two important types of state change dynamics. The first one can be called influence dynamics and the second one migration dynamics. In influence dynamics, agents do not change their location, but they change their state. For example, you may change your opinion from pro something to con something because the majority of your neighbors is also against it, has a con opinion. In migration dynamics, the state that the agent changes is actually the location. That is, an agent may move to another place in the world depending on the current state of the neighborhood. In the lecture on agent-based models, you have already encountered a well-known example of a migration dynamic, Schelling's model of ethnic segregation. We have now seen the three most important principles of a cellular automaton model. To summarize, there is a spatial structure, like on a checkerboard. Second, interaction is local. Agents in a cell only interact with cells in a close neighborhood around them. Third, interaction is modeled as state change. Agents have a state that they can change, and whether and how they change it depends on the states of the other agents in their neighborhood. State change can be both change of an agent characteristic or change of the location of an agent. In the remainder of this lecture, we will look into a simple example of a cellular automaton model. This is a model for the formation of opinion clusters. We will do this in the next movie.
In this video, we're going to discuss cellular automata. We will firstly talk about what they are before looking at a classic example. We will then discuss individually the different classes of patterns that cellular automata can generate before wrapping up with a talk about their significance as a new approach to mathematical modeling. Cellular automata are algorithmic models that use computation to iterate on very simple rules. In so doing, these very simple rules can create complex emergent phenomena through the interaction between agents as they evolve over time. To illustrate the functioning of a cellular automaton, we will take an example from probably the most famous algorithm called the game of life, devised by the mathematician John Conway. The game of life is played on a grid of square cells. A cell can be live or dead. A live cell is shown by putting a mark on its square. A dead cell is shown by leaving the square empty. Each cell in the grid has a neighborhood consisting of all adjacent cells to it, and there are just 3 rules governing the behavior of an agent. 1. Any live cell with fewer than 2 live neighbors dies, as if caused by underpopulation. 2. Any live cell with 2 or 3 live neighbors lives on to the next generation. 3. Any live cell with more than 3 live neighbors dies, as if by overcrowding. 4. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. So let's input a starting condition and run the program to see what we get. This pattern is called still life, for obvious reasons. Its product is probably the most simple class of pattern, called Class 1, where nearly all of these patterns evolve quickly into a stable, homogeneous state, and any randomness in the initial pattern disappears. The second class of pattern we may get is where the system evolves into an oscillating structure, the simplest of these being a blinker that has a period 2 oscillation. We can also have oscillating structures that cycle over prolonged periods of time. For example, a pulsar has a period 3 oscillation, but oscillators of many more periods are known to exist. Class 3 patterns are random, where nearly all initial patterns evolve in a semi-random or chaotic manner. Any stable structures that appear are quickly destroyed by the surrounding noise. Local changes to the initial pattern tend to spread indefinitely. Here we can get what are called gliders, where a group of cells appear to glide across the screen, and this is a good example of emergence, as we no longer see the simple rules that are producing them, but instead this emergent structure of an object gliding. Lastly, automata can also produce patterns that become complex and endure over a prolonged period of time with stable local structures. With these more complex patterns, cellular automata can simulate a variety of real-world systems, including biological and chemical ones. Since the advent of the game of life, new, similar cellular automata have been developed that can do all sorts of things, such as create fractal patterns, that is, self-similar structures that repeat themselves over various scale of magnitude. Other games create patterns that can reproduce themselves. We might ask, is there anything that these automata can't do? From the perspective of computation, the game of life can do anything that your computer can do. It can count to 100, calculate the volume of a cylinder, or if you wanted to figure out the cube root of 1230, you could encode this into a set of cells on the automata and have it compute the value. The game of life, as simple as it is, has proven by computer science to be capable of universal computation. Lastly, we will talk about the significance of cellular automaton as a new approach to mathematical modeling. Von Neumann and Ulam originally introduced the concept in the mid-20th century, and then, a few decades later, the popular game of life brought interest to the subject beyond academia. In the 80s, Stephen Wolfram engaged in a systematic study of cellular automata, after which he published a book called A New Kind of Science, claiming that cellular automata could enable a new approach based upon the exploration of these algorithms. But what is behind this big statement about these simple programs creating a new kind of science? One assumption within modern science is that simple rules can only create simple phenomena, and thus, inversely, complex phenomena must be the product of complex rules. The advent of chaos theory during the past few decades revealed this to be an invalid assumption, as simple systems like a double pendulum proved to be capable of generating complex and chaotic behavior. It is now increasingly accepted that complexity may not be the product of complex rules, but in fact emerge out of an interaction of simple rules as they evolve over time. Cellular automata are the tools that capture and embody this paradigm within science. Secondly, ever since the rise of modern science some 400 years ago, equations have been the dominant form of mathematical models through which we have encoded so-called scientific laws of nature. There are many valid applications for equation-based modeling, but they also have their limitations. They present a somewhat static picture of the world in a state of permanent equilibrium. This is most clearly exhibited within economic models that describe markets as always moving towards an equilibrium state between supply and demand. But in reality, many complex systems like ecosystems and societies are only at or near equilibrium when they are dead. Things are constantly changing. New technologies are invented, startups are disrupting the status quo, and so on. Non-equilibrium phenomena of this kind are not well modeled by equations and are best described through the evolutionary dynamics that shape them, with cellular automata again being well designed to capture this. We will wrap up then by saying that cellular automata are an alternative computation modeling method based upon algorithms that iterate on simple rules to try and simulate complex phenomena. The primary classification of cellular automata are numbered 1 to 4 in order of the complexity that they can sustain, as they go from stable to periodic oscillation to chaotic and complex patterns of behavior. We have also talked about how they are better suited to modeling phenomena that are the product of evolutionary dynamics and have emerged out of the interaction between their parts, as is typically the case for complex systems.